Hi, kiddos. Okay, so I'm sure you can tell by looking past me that I'm in a different location. It ends up in the last video right in the middle of talking to you about one of the best subjects there is, mutualism. My phone died. Sorry about that. So what I've done, I've come home, I've charged it up, and we're ready to go again. And so we've got, 12 more slides. So we'll have a few more videos, and I'll get this chapter 3 completed. So anyway, so here we are. We were on this slide right here, species interactions, and we were talking about mutualism. I remember. So we were talking about mutualism, and I had said that in a mutualistic relationship, unlike a predator-prey or a parasite, in the mutualistic relationship, we had said that both partners benefit. And I know I was talking long about the time we lost it. I was talking about lichens. I was talking about lichens, and I'd said they're this weird sort of organism that is a fungus and an algae, or another kind of a thing called blue-green algae. They have this mutualistic arrangement where neither one can survive without the other. So they both benefit. And so in a symbiosis, both partners benefit. Okay, so we also have a situation, and in some cases, people say commensalism might not really be true. It might be a very minor negative to one individual. But in a commensalism, you have one partner who benefits, and the other, it's no benefit or damage. There's no damage either. And so when I think of commensalism, I think of orchids. You might not know the first darn thing about orchids, and if you don't, then that's a crazy statement, right? But if you know about orchids, you know that in the forest, they will grow on top of the limbs of trees. And so they will grow in a situation on top of limbs, and because of their roots, they will build up essentially dirt on top of the limbs of trees. So the orchid definitely benefits. And now the question is, does the tree benefit or not? Or maybe it hurts the tree, having this up there. So for the sake of an argument, we're going to say the tree doesn't benefit. So it doesn't hurt the tree, it doesn't help the tree. But the orchid gets a place to live. Now there's evidence to suggest that maybe the tree benefits from that soil that's there. But anyway, that's what a commensalism is. And I'd already mentioned, I was just looking here at the slide, species interactions, and I see we had parasites, and I'd already mentioned that that's really a form of predator-prey. So that one really shouldn't even be on this slide. So, hey, we're going to slide 8. Yes! Okay, we are the Keystone State, and we're going to talk about Keystone Species. They don't live here. But anyway, that's what we call them. A keystone species is one that changes their environment. They change their environment so much that they change the competitive balance of other species. And an example of that, and you'll agree, they don't live here, are prairie dogs. Prairie dogs live out west. But what do? They're those cute little rodents that have holes in the ground, and they make a mound, and they stand up on the mound and look around for predators. And you know what else they do? Because that mound is only, 6 inches high maybe, because of that, they have to make sure that the plants around them aren't so high that they can't see over them. So they go out there and they cut off the plants. And so in a prairie where you don't have prairie dogs, you get really tall plants that are going to shade out the shorter ones. But here, if you have a prairie dog who is snipping off all the tops of the tall plants, it gives the smaller plants, the shorter plants, an opportunity to outcompete the tall plants. And so you get completely different plant communities in prairie dog towns because of the action of these little rodents. And so they are keystone species because they change their environment. And not only do they change their environment, they change the competitive balance in the species that normally occur there. And that is the definition of a keystone species. And it goes on to say they exert their influence by changing the competitive relationship of other species in their community. I have a really great video there. Make sure you watch it. In addition to this video, watch that video. You'll see it on a test. So anyway, if make sure you look at it. All right, I'm gonna keep on keeping on. We're gonna move right on ahead to slide 9. We're clicking them off now. All right, so we have this slide right here. It is the growth of species populations. And it says something about R-selectors. And so it ends up, when you start looking at the way species populations grow, in some species, like that fly that we were looking at there, the thing that controls them, or that controls their reproduction, is just the speed with which they can lay eggs, right? They can populate an area very rapidly because what is controlling their population is their rate of reproduction. And so what we call them is R-selectors. And what that's meaning is that their rate of population growth, the number of individuals, the rate of population growth is controlled by how rapidly can they reproduce. And it's amazing how fast they can reproduce. So we have an example here of a single housefly, a female, who has mated, and she lays 120 eggs. 34 days later, those eggs hatch out, and after the 120 eggs were laid, 54 days later, those eggs have hatched out, and the next babies are laying their eggs. So it's 54 days from the day that the first fly laid its eggs before those babies lay their eggs. And then another 54 days, right? And so this is what we call exponential growth. Do you know, if you start out with 1 and you say half of the babies will be female and they'll lay 120 eggs each time, if you carry that out at the end of a year, do you know how many flies you'll have? More than you expect. 5.6 trillion. That's with a T. 5.6 trillion. And so what happens if we look at population growth, and so you see we have time across the bottom and then the numbers of individuals, the fly will start reproducing, and it reproduces faster and faster and faster until what happens? Until they run out of food, and then a whole bunch of them die. Most of them die. So they have this boom to bust kind of life history. Nobody worries about it because they're flies. Everybody hates flies, right? So the rate, what limits them is the speed at which they can reproduce, and then occasionally they get a population crash. So then we have the other extreme. We have the other extreme which is what they're called is K selectors. So here you can see some really big fish. That's a bluefin tuna. These are tunas, and they're very long-lived species. And you know what the K stands for? It's the carrying capacity of the environment. So once you get to the number of individuals that is supported by the food and the resources that are available in the environment, then what happens is if the population gets a little bit above that, they don't have as much food as they really need, and so then reproduction slows a little bit and they drop down, and then they're below the carrying capacity, and so life is good. You can eat extra, get seconds, so to speak, and then the population comes up. And so what happens is we have the carrying capacity, what am I doing? This stupid thing. The carrying capacity of the carrying capacity of the environment, they overshoot, undershoot, overshoot, undershoot. The population, the numbers, they don't crash. They just oscillate around the carrying capacity. I've got to try and move this thing back over. This is one of these notebooks where you can use your finger. I don't much care for that, but anyway, so that's the other extreme. So it's not how fast can they reproduce. They don't produce that many babies. The question is how much can be carried by the environment. And in this case, so what about the housefly? Do you think that she's doting on her babies? No, she finds some dog poop in the yard, some kind of poop or some dead animal, right? Lays her eggs and she goes off and, wherever a fly goes. In the case of K selectors, oftentimes there is parental care, and there's fewer young because they don't need to produce this giant number because they have a different survival strategy. Now, what we realize is, and if you look at even at this graph right here, you can see that looks a lot like, at low population numbers, that looks a lot like an R selector, right? And so then what happens as you get closer and closer to the carrying capacity, you start getting resistance. I said, the environment gets tough, so you get environmental resistance because food starts to become scarce. And so now sort of the more modern way of thinking of population growth especially with the K selectors, is that it's really what we call a logistic growth curve. It's kind of an S curve. At low population numbers, they're logarithmically growing very rapidly, and then as they approach the carrying capacity, it slows down. And so what we call this is density dependent growth. It means the density of the individuals, as that density increases, as the number of individuals increases, which is increasing density, the population growth slows down. Okay, I'm going to stop right here. We've been 14 minutes, and we'll talk about survival on the next slide.